everyone. This is the topic 2, water resources analysis and evaluation. In this session, we will start with remote sensing and geographic information system tools. You can you remember in the first session we talked about the hydrological cycle. This is a new diagram produced by the USGS, the United States Geological Services, and we talked about the human influence on the hydrological cycle. And we emphasize the necessity of evaluate the water resources and to estimate the availability of water resources in the territories where we are working. And in this case, this is a new diagram from the United Nations. It shows the necessity of global data to promote local action. This is a general framework for water management at this time when we need to mobilize action, and the concept of nature-based solutions is a concept for the new water management paradigm. To enhance the nature-based solutions, we need to acquire and analyze global data in order to promote local action. When we talk about global data, we refer to, for example, satellite images, remote sensing information, different types of sensors that provide us a lot of information to make decisions about our water resources. For example, this is a general view of the Earth. This image was taken by the Discover satellite, and this image is available on the internet and is available for all the people around the world. We can see different type of cloud formations, different types of water transport in the atmosphere, and this is only one of the wide range of satellite products we have for water resources evaluation. What is remote sensing? It's the process of detecting and monitoring the physical characteristics of an area by measuring its reflected and emitted radiation at a distance, typically from satellite or aircraft. Special cameras collect remotely sensed images which help researchers sense things about the Earth. Some examples are cameras on satellites and airplanes take images of large areas of Earth's surface, allowing us to see much more than we can see when standing on the ground. Sonar systems and camera on satellites can be used to make image of temperature changes in the terrain or in the ocean surface. And we have a lot of specific uses of remotely sensed. For example, in this image, we can see the capital city of Uzbekistan. We can see water reservoirs and field irrigated fields downstream the reservoir, and are examples of specific uses of remotely sensing images. For example, to monitor large forest fires, to tracking clouds, to help predict the weather, to monitor the growth of a city or the changes in agricultural surface through the years, and we can use satellite images to establish digital elevation models of the ocean floor, of the earth terrain, etc. We have mentioned sensors mounted on satellites, planes, drones, and ground-based platforms in order to monitor land cover regionally and globally. And now we will talk about how to assess the global water cycle using different types of satellite missions. We have this table. We have included programs, organizations, satellites, missions, and the electromagnetic spectrum, the bands which are used by those specific sensors, and the different and general characteristics. For example, for the World Weather Watch program operated by the World Meteorological Organization, we can find satellites missions as EUMETSAT, Meteosat, GEOS, NOAA 19, etc., etc. Those missions operate in the visible and the infrared spectrum. For example, we can appreciate this image. This image is centered on 0.6 micrometers of the visible spectrum. This is a full disk image of Europe and Africa obtained with the Meteosat second generation constellation. This mission is used mainly for meteorological models and predictions. The European Organization for the Exploitation of Meteorological Satellites, EUMETSAT, currently operates the Meteosat second generation constellation, formed by Meteosat 9, 10, and 11 in geostationary orbit over Europe, Africa, and the Indian Ocean. Those satellites are located about 36,000 kilometers over the ground. Meteosat imagery is crucial for nowcasting, which is about detecting rapidly developing high-impact weather and predicting its evolution a few hours ahead in support of the safety of life and property. Observations are also used for weather forecasting as input to numerical weather prediction models and for climate monitoring. This is another satellite mission called Aqua. Is a NASA Earth Science satellite mission named for the large amount of information that the mission is collecting about the Earth's water cycle, including evaporation from the oceans, water vapor in the atmosphere, clouds, precipitation, soil moisture,
sea ice, land ice, and snow cover on the land and ice. Additional variables also being measured by these satellites include radiative energy fluxes, aerosols, vegetation cover on the land, phytoplankton, and dissolved organic matter in the oceans and air, land, and water temperatures. And aqua operates in the passive microwave. Now we will talk about the Landsat program. This program provides the longest continuous space-based record of Earth's land in existence. Landsat data give us information essential for making informed decisions about Earth resources and environment. And here we can see the timeline of the Landsat program, starting with the launch of Landsat 1, finishing in Landsat 9. It was launched on September 27 of 2021, and Landsat 9 will continue the legacy of this important and fundamental program. Since the launch of the first Landsat satellite in 1972, the mission's archive has grown to contain than 8 million images. And now most of those images are available to the public and researchers and technicians. And Landsat 9 data will add information to this archive, enhancing our understanding of Earth in different ways, from tracking water use in crops in different parts of the world to monitoring deforestation in the Amazon basin or in the tropical forest in Africa, South Asia, etc., etc. We can also measure the speed of Antarctic and Arctic glaciers melting, and decision makers from across the globe can use the freely available Landsat data to better understand the environmental systems and to forecast global and regional crop production, and to plan an adequate response to natural disaster and more. In the case of Landsat 9, this satellite captures scenes across what 185 kilometers wide. Each each pixel in these images is 30 meters across, similar to the to a baseball camp or baseball court. Its instruments collect images of Earth's landscapes in visible, near and short-wave infrared and thermal infrared wavelength. We have to mention that Landsat program is a joint effort of NASA and the US Geological Survey. But Landsat develops a critical role for water since 1972, because Landsat data assist the local and global decision making with four main purposes: locating water resources, assessing water pollution, managing watersheds, and allocating water resources. For example, we can see in this image the Rio Cauto Delta. This picture was taken in 2020. It's a Landsat 8 image, and this picture is a part of a global study of the routes for global mangrove loss. And the Rio Cauto Delta is an international recognized wetland of importance. And this delta is home to numerous species of mangroves. We have to mention a very important sensor and a very important satellite mission operated by the National Oceanic and Atmospheric Administration of the United States. The Advanced Very High Resolution Radiometer, AVHR, is a cross-track scanning system with 5 spectral bands having a resolution of 1.1 kilometer and a frequency of Earth scans twice per day. And for example, in this image, we can see the developing process for the Hurricane Andrew. The objective of this instrument is to provide radiance data for investigation of clouds, land water boundaries, snow and ice extent, ice or snow melt inception, day and night cloud distribution, temperatures of radiating surfaces, sea surface temperature and vegetation classification and greenness through passively measured visible near-infrared and thermal infrared spectral radiation bands. And it is important to mention the MODIS instrument. MODIS, or Moderate Resolution Imaging Spectroradiometer, is a key instrument aboard the Terra and Aqua satellites. We've mentioned previously the Aqua mission, and Terra MODIS and Aqua MODIS are viewing the entire Earth's surface every 1 to 2 days, acquiring data in 36 spectral bands or groups of wavelengths. It is important to consider that Terra's orbit around the Earth is timed so that it passes from north to south across the equator in the morning, while Aqua passes south to north over the equator in the afternoon. And this data improves our understanding of global dynamics and processes occurring on the land, in the oceans, and in the lower atmosphere. MODIS is playing a fundamental role in the development of validated global and interactive Earth system models able to predict global change accurately enough to assist makers in making sound decisions concerning the protection of our environment. And in many environmental emergencies, we can see governmental organizations are assisted by this by those information instruments based on Modi's imagery. For example, this is an image taken on 29th of June of this year, and we can see Hurricane Adrian. This hurricane became the first hurricane of the 2023 Eastern Pacific hurricane season, and we can see this hurricane located off the coast of southern Mexico. Okay. We are going to talk about the Copernicus program. It is the Earth observation component of the European Union space program, looking at our planet and its environment to benefit all European citizens and the global community. It offers information services that draw from satellite Earth observation and in situ data, non-space data. And we have vast amounts of global data from satellites and ground-based, airborne and seaborne measurement systems, provide information to help service providers, public authorities, and other international organizations in order to improve European citizens and global community quality of life and beyond. It is important to emphasize that the information services provided are free and openly accessible to users distributed across the entire world. And Copernicus services are related with the atmosphere services, marine management, land monitoring and management, climate change, security issues, and emergency issues. The European Space Agency is developing a new family of missions called Sentinels, specifically for the operational needs of the Copernicus program. Each Sentinel mission is based on a constellation of satellites to fulfill revisit and coverage requirements, providing robust datasets for Copernicus services. And These missions carry a wide range of technologies, such as radar and multispectral imaging instrument for land, ocean, and atmospheric monitoring. And on the picture on the right, we can see different artifacts that belong to the Sentinel family. We are talking about the Sentinel-1, Sentinel-2 satellite, Sentinel-3, Sentinel-4, Sentinel-5B, and the Sentinel-5, and finally the Sentinel-6. Let's start with the Sentinel Copernicus Sentinel-1. This mission provides all-weather day and night radar imagery for land and ocean services. The twin satellites Sentinel-1A and Sentinel-1B were respectively launched on April of 2014 and April of 2016. And for example, this is an example of its application. This picture shows how the William Glacier on the Antarctic Peninsula has retreated since 1955, roughly 3 kilometers in all. The last two retreat lines corresponding to 2016 and 2021 are based on Copernicus Sentinel-1 satellite data, and the very early years before the advent of the satellite era are based on aerial observations. What about Copernicus Sentinel-2? This mission provides high-resolution optical imagery for land surfaces. It provides, for example, imagery of vegetation, soil and water cover, inland waterways and coastal areas. Sentinel-2 also delivers information for emergency services. There are twin satellites, Sentinel-2A and Sentinel-2B, that were respectively launched on June 2015 and March 2017. For example, these images were acquired by Copernicus Sentinel-2 satellites on two moments, June 2022 and June 2023, the past 14th of June, and these images show the Canelon Grande Reservoir in Montevideo, Uruguay, which is going through an unprecedented water crisis. Uruguay at this moment is facing its worst drought in decades, caused by a combination of factors: precipitation deficits, above average temperatures, and recurrent heat waves. And the drought is resulting in a water shortage in the Montevideo metropolitan area, where a state of emergency has been declared. Some newspapers are declaring that Montevideo has reached its own day zero. at this opportunity. We are worried about this situation. What about Copernicus Sentinel-3? This mission provides high accuracy optical radar and altimetry data for marine and land surfaces. It measures variables such as sea surface topography, sea and land surface temperature, ocean color, and land color with high gain accuracy and reliability. The twin satellites Sentinel-3A and Sentinel-3B were respectively launched on February 2016 and on April 2018. EUMETSAT, we mentioned it before, operates the satellites and delivers the marine mission, while the European Space Agency delivers the land mission. On the right, we have a picture showing the global land surface temperature as measured by Copernicus Sentinel-3. Land surface temperature is an essential climate variable that describe processes such as energy and water exchange between the land surface and atmosphere and plant growth. And this information has become fundamental to monitor heat waves and other temperature anomalies during the last years in many regions around the world. The Copernicus Sentinel-4 will provide data for atmospheric composition monitoring. Its objective is to monitor key air quality trace gases and aerosols over Europe at high spatial resolution with a fast hourly revisit time. It will be a payload embarked on EUMETSAT's third generation mission. And the Copernicus Sentinel-5 will also be dedicated to atmospheric composition monitoring. To be launched in the coming years, it will provide accurate measurements of key atmospheric constituents such as ozone, nitrogen dioxide, sulfur dioxide, carbon monoxide, methane, formaldehyde, and aerosol properties. Here we have the Copernicus 5P. P of means precursor. This is a satellite mission launched on October 2017 to fill the gap and in order to provide the data continuity until the launch of Sentinel-5. Sentinel-5P provides measurements of key atmospheric constituents such as dioxide, nitrogen dioxide, methane, and other atmospheric constituents. For example, on the right, we can see the desert dust plume over the Atlantic observed by two satellites, Aelus and Sentinel-5 precursor. The underlying Sentinel-5P aerosol index in fluorescent yellow and green, which indicates the extent of the elevated Saharan dust plume over the Atlantic, has been overlaid with information from AELUS aerosol and cloud data. In yellow, parts of the laser light are scattered and absorbed by the Saharan dust. These data are so important for air quality models used by, for example, the Copernicus Atmosphere Monitoring Services. For example, when we have a lot of Sahara dust concentration, it might affect many water sources in our region. That's the reason why it is important to monitor this quality factor, air quality factor. And the Copernicus 6P provides high accuracy altimetry for measuring global sea surface height, primarily for operational oceanography and for climate studies. It is a cooperative mission developed in partnership between Europe, the European Union, the European Space Agency, and EUMETSAT, and the United States agencies, the National and Oceanographic Agency, and NASA. It was launched in 2020. Copernicus Sentinel-6 is taking on the role of radar altimetry reference mission, continuing the long-term records of prior satellite missions. And Sentinel-6 brings, for the first time, a synthetic aperture radar into the altimetry reference mission time series. We've talked about many examples of how we can apply satellite data to water management. It is important to consider, for example, the Copernicus products application in support of the United Nations Sustainable Development Goals. Copernicus is a powerful instrument to help monitor these indicators and support the implementation of the Sustainable Development Goals. We have an unprecedented amount of data and information generated by these programs that supports decision makers in developing adequate policies to achieve the goals and facilitates the monitoring of the Sustainable Development Goals. It is important to emphasize that it is available on a full, free, and open basis, which contributes to reducing the cost of monitoring indicators and also allows for the development of operational products and services supporting the Sustainable Development Goals. For example, related with the Sustainable Development Goal number 11, Sustainable Cities and Communities, here we have an example, an example used by the Copernicus Emergency Management Service. It provides information for emergency response in relations with different types of disasters, including floods, as well as related prevention, preparedness, response, and recovery activities. As an example of how this emergency service supports emergency preparedness and response, is the activation of its rapid mapping components following floods in Peru in early 2017. These events resulted in more than 100 deaths, caused the evacuation of around 158,000 people, and damaged 210,000 homes. And the maps produced by Copernicus service help it analyze the affected areas and the extent of the floods in real time, allowing the civil protection authorities to target their rescue operations. This is another example to illustrate how the Copernicus products can support the Sustainable Development Goals. For example, related with the SDG 15, Life on Land, we have this image, a cropland classification around the Sousse River in southern Morocco. This is an excerpt of the Copernicus Global Land Cover Map, and we can add additional layers of irrigation plots that have been produced by FAO's Water Productivity Portal. This is an interesting rain-fed cropland and irrigated cropland map using satellite information, mainly Copernicus 2 products.
Well, hello to all of you. My name is Arauco Schiffman. I work in INTA IPAF NEA. Laguna Nainec is the town. Formosa is the province. Argentina is the country. And I will share a presentation with you. Well, I will talk about the Module 3, Water Access and Use, and the topic does about harvesting water. Specifically, I will talk about the water resource analysis and evaluation and the collection and catchment of surface water and groundwater. In the first place, I will talk about the three components that a system of collecting water needs to in order to work properly. We have several methodologies for resource diagnosis and survey. We need to know how much water we have in a certain place in order to manage that water properly. So we have, in the first place, the physical component. Then we have the water resource quantity, the quality, and the opportunity. How much water we have in different places, the quality of that water, if the quality is for human consumption or animal consumption or irrigation, the topographic conditions of the place where the water is, the spatial distribution, the climate, the soil, and the vegetation of that place. The second component that we have is the social component. How many people are involved in different places where the water is required. The requirement of that people, the population growth, the management, the organization, the agreement to use the water, the economics, the humans and material resources, the existing practice and water rights for the correct use of the water. And when we have the two components that I mentioned, we can do a water system design. That is the catchment, conduction, storage, treatment, and distribution infrastructure for the correct water use. We need to take in mind the tasks required for the operation and maintenance of the water, the rights and the obligations, and the utilization rules. In these slides, we talk about the quantification of the demand. We need to identify the problem, what is the community needs and the technical, and we need to do field trips to know the techniques that we need to do in order to supply the water for that community. What are the requirements? Domestic, irrigation, livestock, individual or community use. So when we have the demand quantification, we can do a quantification of the water availability of that place. The water resource type, if it's surface water, groundwater, or rainwater, and the characterization, the location, the flow, the quality, the interannual and the intra-annual variability of the precipitations. Then we need to know the site conditions, the topography, the slopes, levels, distances, and with all that information, we can do an infrastructure and water system technical design. All of this stuff will allow us to do a water catchment system. The infrastructure depends on the water source. That's because if it's superficial, surface water, Gaussian station, or other techniques to measure flow rate, level, physical, chemical, and biological quality, variability in time, we have streams, we have rivers, and springs. If we have groundwater in a certain place, we can do different kind of practices or techniques to do the surface, the water extractions. Traditional practices like dowsing or water witches, and geoelectric prospection, the vertical electric sounding. And if we only have rainwater, we need to construct roofing and additional structures in order to catch that water. And we need to know the characteristics and the dimensions we need to take in mind. The traditional practices, the dowsing or water witches, consist in, this is a picture from an experimental station of INTA in an arid place in Formosa, in another town of Formosa, where the people, the farmers, don't know any specific techniques, expensive techniques. They don't have expensive techniques, so they use this kind of sticks, or we can use wires to know where is the groundwater. You have to believe in this because it's not a scientific method. But if we have some funding for do some research, we can do a geoelectric prospection, the vertical electrical sounding, like this one that we have, like we can do an electrical state of the soil so we can search resistivity layers. When we have layers with more resistivity, there is more chance that the water don't flow freely in that layers. So we need to search for layers with low resistivity, generally the sand layers. And we have here the rainwater catchment, where we need to do some structure, properly structured with the proper dimensions to catch the water, like the houses with thin roof and gutter, and conduct that water to cisterns or tanks or anything. When we need to know the water that is needed in some place, we need to do a survey. This is the first source of information. When we talk to the people, and the people say, well, I have this pump, I have this excavation. The people talk to us, to the technicians, in order to know the capacity, the water capacity, the possibilities for store water. The same for apply for the quality. How is the water that the people have? And the localization of the water, the distance to the bathroom, the distance to growing areas, etc. So we can do a project to fund a water system for farmers. And also here we have the need for the animals. Different kind of animal species have different demand for water, for drinking water. So we need to plan the water that we need to collect and to store for the water consumption of the animals. The same for the people. Here I can show you some water collection and catchment structures. As I was saying previously, first we have the surface water. The surface water consists of rivers and streams catchment using pumping systems, and springs protection, like is useful for the Caribbean geography. We have the rainwater catchment through the roof, and the rainwater can be stored also in excavated tanks, farm dams, reservoirs, etc. And additional technologies are the solar distillers, like the picture at your right. Is a technique to remove the salt from the water to the sun energy, solar energy, and the biosun filter or similar. Here I can show you some pictures of some places of Argentina. This is from the Misiones province, where they have similar geographical characteristics like in the Caribbean countries. They have big slopes and soils that sometimes don't permit the storage of water because they are too sandy. And they use different technologies in order to collect the water. This case is a groundwater abstraction using drilling wells or boreholes, where where there is in places where there is groundwater, that we know that is groundwater. And this technology is used in the Misiones province, the water collection and catchment from spring protections. This is the springs are water that emerge at the surface. And we need to do some kind of structures to, in the first place, identify where is the spring, and then protect that springs from contamination, of different kind of contamination. And then we can conduct that water to another place to storage. So there are here we can see the different steps that we need to do in order to protect that spring. This is a picture from the Misiones province where that technology is used in that place. And I want to share with you this kind of technology that is used in the Misiones province and how our institution, INTA, helps the people in the funding of projects to permit that the people have different kind of water for consumptions. This is just an example that in the last 5 years, more than 300 protect springs were realized with distribution networks, totaling more than 3,200 rural families. This is a picture of that kind of structure. And these are different pictures of different technologies. This is the water wheel that is a technology for pumping water from a river to a different places that are at a certain distance. And I will this was my presentation, and I want to say thank you very much for your attention, and hope that this presentation was useful for you. Thank you.